Redox reactions are extremely important in modern society. For example, modern batteries, galvanic cells, are all based on redox reactions. This is an important area to understand. Let's begin with what are redox reactions. A redox reaction is any reaction that involves the transfer of electrons from one species to another. That transfer of electrons is key. So for example, when sodium and chlorine react, it's a redox reaction. Sodium loses electrons and chlorine gains electrons. They are transferred from the sodium to the chlorine. So we say the sodium has been oxidized. It has lost electrons. And we say the chlorine has been reduced because it's gained electrons. So electrons are transferred from sodium to chlorine to form sodium chloride. And what is sodium chloride? It's actually a big network or lattice of positively charged sodium ions and negatively charged chlorine ions. It's an ionic compound. But the sodium are positively charged because they've lost electrons. Chlorine is negatively charged because they gained electrons. And that transfer of electrons is what makes this a redox reaction. Let's consider another example of a redox reaction. If we place a solid zinc plate into a copper sulfate solution, what will happen? Well, we know that the zinc will move into the solution and form zinc 2 plus ions. And we know the copper will deposit on the plate as solid copper. So the zinc is displacing the copper from the solution. But what's actually happening in that reaction? How is zinc forming 2 plus ions? It's doing that by losing 2 electrons. So the only way zinc is forming these positively charged ions is by losing 2 electrons. Where are those electrons going? The copper is gaining 2 electrons. That's how it's forming solid copper. So here the zinc is being oxidized. It's gaining electrons to form zinc ions. And what's happening to the copper? It's being reduced. This is an oxidation and reduction reaction, or a redox reaction. And it's involving the transfer of electrons. Zinc is losing the electrons, copper is gaining them. You should be able to see that since oxidation is the loss of electrons and reduction is the gain of electrons, these always happen together. One species loses electrons, the other is gaining them. But what if we could separate the oxidation and reduction reactions so they happen in different places? Theoretically, we should be able to do that. I should be able to have zinc being oxidized to form zinc 2 plus and 2 electrons. And in a different spot, I should be able to have copper gaining those 2 electrons to form copper, as long as there's some way for these electrons to move over to the copper. And since electrons can travel in wires, it's possible to have zinc in one spot. We'll need some sort of solution so these zinc ions can go into solution. And to have copper in a different spot, I'll need some sort of solution of copper ions and some way that some sort of electrode so that I can join it to this one to make a path for the electrons. But theoretically, I should be able to have the oxidation reaction and the reduction reaction happening in different places, as long as I provide a path for the electrons to move across. If I separate them, I get 2 different half equations to describe what's going on. On one side, we've got zinc, which is being oxidized by losing the electrons. In the other half equation, is copper being reduced by gaining the electrons. What's the overall reaction? If I add these together, this one, the first one, plus the second one, if I add those 2 reactions together, I should get the overall reaction. And what do we get? Zinc, I'm adding everything on the left first, plus copper 2 plus 2 electrons goes to, I've got my zinc ions plus 2 electrons and my copper. So if I add everything on the left and everything on the right, that's the overall reaction that is happening. I can cancel the electrons because they're on both sides. And what have I got? Zinc is forming zinc 2 plus, copper 2 plus is being reduced to copper. The overall reaction is zinc plus copper 2 plus ions is going to zinc 2 plus solid copper. And there's my net ionic equation. So I can separate the oxidation and the reduction parts of the reaction into two sort of half cells, move them away from each other as long as there's a path for the electrons, and the overall reaction is still the same. It's just happening in two different places. How do we do this in practice? Normally, we take the first metal, in this case zinc, and we put it in a solution of its ions, zinc sulfate. So that's got zinc 2+ ions in here. There's the zinc and the zinc 2+. And we take a different container with the other metal, in this case copper, in a solution of its ions. So we've got copper 2+ in there. Then we join them with a wire that provides a path for electrons to flow, so that if zinc gets oxidized to zinc 2+ and loses electrons, the electrons can move through the wire to get to the copper, and that way the copper, when it gains the electrons, copper 2+ can form copper by gaining electrons. So we can join two of these half cells into what we call a galvanic cell. We do need a salt bridge in the middle, and you can look at why that's important, but we can join them to form a galvanic cell, and we will get a flow of electrons moving through this wire. What have we made? A battery, just by joining a metal electrode in a solution to another metal electrode in a solution of its ions. It's a galvanic cell. What happens if we join different metals and different metal solutions? Well, in the first example, I had zinc in a zinc 2+ solution. I joined it with a wire and a salt bridge to copper in a copper 2+ solution. This is how we often represent our galvanic cell, with these vertical lines, meaning you've got an electrode in solution, and the two vertical lines indicating you've got the wire going across and the salt bridge. What I found when I did that, and I measure the voltage, I get 1.10 volts. If I take two different metals, here, copper and silver, and I join them in the same way, I've still got copper ions here with an electrode in it. I've got the silver in a solution of silver ions. I can still get oxidation reduction. It's all the same, but what happens? When it's copper in copper 2+, joined in a galvanic cell with silver and silver ions, I get a different voltage. I get still positive, so this one was positive, 0.46 volts. Now that voltage, or EMF, the electric potential, is actually measuring sort of the push that's moving electrons from one electrode to the other. Here with zinc and copper, there was a bigger potential difference, or a bigger sort of push that is moving the electrons from one electrode to the other. With copper and silver, it's lower. And so we find we get different voltages between different pairs of electrodes. It's quite easy to understand why there might be a different sort of push on the electrons. Let's consider that I have joined potassium as one electrode, potassium in a solution of potassium ions, and copper as the other. Potassium is extremely easily oxidized. It's a very reactive metal. So if I did join a cell like this, potassium would lose electrons very easily, and they would move to the copper. So the copper would be reduced, the potassium would be oxidized, but I would expect that reaction to happen very quickly, and there would be a very big push on electrons. If I join something like iron as one half cell, ion in iron solutions, a solution, with copper as the other electrode in a solution of copper ions, I would still expect, because iron is more easily oxidized than copper, I would still expect the electrons to move that way. The iron will be oxidized still, the copper will be reduced, but I would not expect this reaction to happen nearly as quickly with iron as it does with potassium, because potassium is just so reactive and loses electrons so easily. So I would expect that with potassium and copper, I would expect a very high voltage if I set up a cell like that, a very big, strong push moving the electrons from one to the other. But if I set up iron and copper, I would expect a lower voltage. And it makes sense. It's going to depend on how easily one of them is oxidized and the other is reduced, because that's what's causing the electrons to be moved. The previous slide showed us that potassium is more easily oxidized than iron. A different way of saying that is it's harder to reduce potassium than iron, because oxidation and reduction are opposites. So it's easier to reduce the iron than the potassium. It's easier to oxidize the potassium. Now, chemists want some standard way of measuring these things. How can we measure how easy it is for reduction to happen at a particular electrode, or for a particular reduction reaction to take place, or oxidation? It's basically the same thing, they're just opposites. So what we've decided to do is to use the reduction of hydrogen as a standard that we compare everything else to. For every other electrode, we look at how easy is it to reduce that electrode compared to hydrogen, or how hard is it? The half equation for the reduction of hydrogen, what are we actually comparing it to? We take hydrogen gas, it gains electrons, so it's reduced, and it forms hydrogen ions. How do we actually set up an electrode like this? Because it's a gas, it's actually quite difficult to have a gaseous electrode. So what we do instead, we take a solution and we put an electrode in it, but we can't use a hydrogen electrode. Instead, we use platinum. We do that because platinum is very unreactive, so it's not going to interfere with the reaction, but it's highly conductive of electricity, so it will allow electrons to flow to the other half cell. So we use a platinum electrode, and then we've got to make sure we've got a supply of hydrogen and hydrogen ions, or hydronium. So we bubble hydrogen gas over that electrode. That makes sure that there's hydrogen there so that it can be reduced. And we have an acidic solution so that there's hydrogen ions in there. That way we've got the hydrogen gas and the hydrogen ions, and the hydrogen could be oxidized, it could be reduced when we join it to another cell. So this is just a way of setting up a half cell that has hydrogen there, and we join it to other things. For example, over on this side, we could put copper in copper 2+ solution, and this would allow us to measure how easy is it to reduce copper compared to hydrogen. We would measure the voltage between them. So we measure every other reduction potential, which is just a way of talking about how easily something else can be reduced. We measure them all compared to hydrogen. For a particular electrode, in my example I've put copper here, but for a particular electrode, if I get a positive measurement there, positive reduction potential, then it will be reduced when it's joined to hydrogen. It's more easily reduced. If I get a negative value, then that means it's harder to reduce it. So when I join it to hydrogen, it would be oxidized. The hydrogen would be reduced. We have recorded all of these standard potentials for different common electrodes, and we've listed them in a table compared to hydrogen. You can see in the middle here, hydrogen is 0. That's by definition, because that's what we're comparing everything to. If you look at the things above it, you can see that these all have a negative voltage. The ones below it all have positive voltage. What does that actually mean? Positive reduction potential means more easily reduced than hydrogen. The ones at the top, negative, means harder to reduce. Now what does that mean? If I add something that's higher up the list, something higher up here, as one half cell, and I join it to something lower down the list, what would I expect to happen? Well, the one at the top is harder to reduce, the one at the bottom is easier to reduce. So I would expect the one that's lower in the list to be reduced, and the one at the top that's higher up would be oxidized. What's that actually mean? Well, oxidation is losing electrons, so I would expect electrons to be moving from the half cell that is higher up in this list to the one that is lower, because the one that's higher up is more easily oxidized. It will lose electrons and it will move to the one that's lower in the list. If we've got electrons moving like that, we can then predict which electrode will be positive and which will be negative, because which way do electrons move? Electrons are attracted towards positive, so this is going to be the positive electrode. This is the negative electrode. In other words, if I join something lower in the list to something higher, the Lower one will be the positive electrode, the higher one is the negative. We also can give the special names for these. Reduction is happening down here at the positive. Remember red cat and ox. So red cat, reduction happens at the cathode. And oxidation happens at the anode. So I would expect if I joined two of these half cells together, the one that is higher in the list will be the anode, negatively charged. The one lower in the list will be the cathode, positively charged. So you can see how enormously helpful this list is. By looking at where each metal or reaction or half cell is in this list, I can predict which will be oxidized and which will be reduced, the voltage, which will be positive, which will be negative as an electrode, which is the anode, which is the cathode, which way electrons are flowing. Not only that, but if I take the difference, so let's take an example here. We've got magnesium being reduced here, minus 2.36 volts. That means it is very difficult for magnesium to be reduced compared to hydrogen. Let's say I join it to something lower in the list, like silver down here. Silver, 0.8 volts. It means it is very easy for silver to be reduced. So magnesium 2 plus, when it is reduced, the voltage is minus 2.36 volts. Silver, when it is reduced, the voltage is plus 0.80 volts. What happens if I join these two half cells? The voltage when I join them is going to be the difference between these two numbers. In this case, because this one is negative, what's the actual difference between these numbers? It's 3.16 volts. I would expect if I joined a magnesium half cell and a silver half cell, I would get 3.16 volts. Silver is going to be reduced and it's the cathode. Magnesium is going to be oxidized and it's the anode. What would actually happen? Silver will gain electrons, that's reduction, to form solid silver. Magnesium will be oxidized by losing 2 electrons. And you can see why we end up with 3.16 volts. If magnesium is reduced, the voltage is minus 2.36 volts. But it's not going to be reduced, it's going to be oxidized. So we're actually going to have the opposite voltage because we've got the opposite reaction. It'll actually be plus 2.36 volts. So one reaction is producing plus 2.36, one is producing plus 0.8. We end up with overall 3.16 volts. Now, even if you don't understand everything that's going on, you can see how this table of standard potentials very easily allows you to predict which will be oxidized, which will be reduced, the voltage, identify the anode, cathode. It is a very powerful tool. Let's look at a couple of examples. What will happen if solid zinc is placed in a solution containing tin ions? We've got solid zinc, tin ions. So the zinc is solid, I've got tin ions. All they're really asking me is, will zinc displace tin from solution? Zinc will do that if zinc is more easily oxidized. Now what's the table over here showing me? The ones at the bottom have a much higher reduction potential. They will be very easily reduced. The ones at the top are much more easily oxidized. So really, I've just got to see, is zinc higher up the table than tin? If zinc is higher up this table, then it's more easily oxidized. It will displace the tin from the solution. Well, where are they? Here's zinc. Here's tin. Zinc is higher up. It is more easily oxidized. So I would expect that the zinc will displace the tin from the solution. And what's that look like? Zinc will form zinc 2 plus ions by losing 2 electrons. The tin will gain those 2 electrons to form solid tin. This is an oxidation reaction. This is a reduction reaction. And by explaining it, giving formulas, using the right words, and explaining how I got that from the table, that would show that I understand what is going on. A second question, what will happen if solid tin is placed in a solution containing zinc ions? Well, Now I would expect nothing to happen because zinc is more easily oxidized, but it's already in solution, so it's not going to be reduced. Tin, more easily reduced, but it's already solid tin. So I would expect in that second example, nothing would happen. I'm going to finish with two examples of how we might answer questions on these topics. This is an example. Describe what will happen when solid manganese is placed into a solution of nickel sulfate. Notice this is a describe question. For a describe question, we don't need to give all the reasons, but we should give some detail on what will actually happen. So here's an answer. The manganese will displace the nickel from solution. Now, how did I work that out? I looked over here. Manganese minus 1.18 volts, nickel minus 0.24. Nickel has a higher reduction potential. It's lower in the list, so the nickel is the one that will be reduced. The manganese will be oxidized and move into solution. The manganese will displace the nickel from solution. Now I need to describe what will happen. The manganese will be oxidized to form manganese ions, which will move into the solution, and the nickel ions will be reduced to form solid nickel. This nickel will be deposited as a coating on the manganese electrode or as particles that settle on the bottom of the beaker. The color of the solution may change due to the presence of manganese sulfate in solution. So I've tried to give a lot of detail there. I've tried to use keywords like displace, oxidized, reduced, to show understanding of what is going on. So there's a thorough description. This next question is actually very different. It looks almost identical. Explain what happens when solid manganese is placed into a solution of nickel sulfate. But notice this key word, explain. So it's a very different question. We're not describing, we need to give reasons for what happens. So what could we answer? The manganese displaces the nickel from solution. Same as last time, same thing's going to happen. But now I'm moving on to reasons rather than a detailed description. Because it is more reactive than nickel. Now, if this is just worth 1 mark, that may be all thereafter. But if it was worth more marks or explicitly referred to standard potentials in the question, then I'd need to refer to this table on the left. So let's keep going with our explanation and give more detail. A redox reaction is occurring in which the manganese loses electrons as it is oxidized, and the nickel ions gain these electrons as they are reduced. Now remember, we've got manganese here, and we've got nickel here. Nickel has a higher reduction potential. Minus 0.24 is higher than minus 1.18. That's why it's lower in the table. And remember, these numbers are bigger than these numbers. So it's got a higher reduction potential. It's the one that's reduced. Manganese, higher up in this list, is the one that's oxidized. Okay, so the manganese is oxidized, the nickel is reduced, and there's an exchange, movement of electrons from one to the other. Now, why does it take place that way? I want to refer to this table here. The reduction potential of nickel is minus 0.24 volts. That's from the table here, which is higher than the reduction potential of manganese, which is minus 1.18 volts. This is why the nickel will be reduced and the manganese oxidized. Now notice I've said it's higher when I've compared reduction potentials. In my answer, I'm not going to say manganese is higher up in the table and therefore it's oxidized, or higher in the list. I'm not going to just compare their order in this table. I'm going to compare the actual numbers if I'm answering it. And how do the numbers compare? The reduction potential of nickel is higher, so the nickel is reduced. The reduction potential of manganese is lower, so it gets oxidized. And you can see this is a very detailed answer. It includes all the key words, like it includes oxidized, reduced, displaces, reduction potential. It shows a thorough understanding of the topic, and it's giving reasons because it was an explain question.